The obvious question, why would anyone haul the truck instead of just the load? At a rail terminal in Austria, a driver guides a fully loaded 40-ton semi-trailer directly onto a specialized low-floor rail car. But the driver does not uncouple the trailer and leave. Instead, the entire vehicle, the heavy tractor, the driver's cab, the steel chassis, the wheels, and a tank full of diesel fuel remains part of the rail movement. The driver then walks down the platform to board a couchette sleeper car coupled to the train, spending the transit resting while the locomotive pulls both the cargo and the machinery designed to haul it. To anyone steeped in the logic of modern freight, this arrangement looks incredibly backward. In logistics, revenue comes from the cargo itself, while the vehicle is simply an overhead cost. Hauling thousands of pounds of dead weight, rubber tires, steel frames, tractor cabs, and sleeping drivers violates the basic law of transport efficiency. The railway is spending massive amounts of energy to carry the very equipment that normally competes with it, moving tons of non-revenue producing steel and fuel along with the freight. Yet, these complete vehicle trains run daily, carrying millions of tons across European borders. It is a striking operational paradox, a system that bypasses the standard rules of intermodal efficiency to move the entire road inventory at once. If the goal of intermodal transport is to strip away the truck and move only the container, this system represents a massive, expensive compromise. Why haul the heavy vehicle itself when only the payload actually matters? This operational system is known formally as accompanied combined transport, or more commonly, the rolling highway, Rollende Landstraße in German, or simply RoLa. It operates primarily across three distinct transalpine corridors: the Brenner Pass linking Austria and Italy, and the Lochberg and Gotthard routes running through Switzerland. Together, these mountain passes form the essential, heavily restricted bottlenecks of European north-south trade. The entire process is designed around speed and simplicity at the terminal hubs. When a truck arrives at a RoLa terminal, it bypasses the traditional lifting equipment entirely. Instead of waiting for a heavy crane or gantry system to hoist its container, the driver guides the semi-trailer toward a specialized terminal ramp at the rear of the train. The rail cars themselves are highly specialized, low-floor vehicles, coupled together with fold-down end plates. When these plates are lowered, they bridge the gaps between the individual cars, transforming the entire train into a single, continuous, flush wooden runway. The truck driver simply drives the entire 40-ton rig up the ramp and rolls along the length of the train, parking on the designated wagon. Once the vehicle is secured using lowerable stanchions and wheel chocks, the driver leaves the cab and walks down the platform to board a dedicated passenger or couchette car coupled directly behind the locomotive. During the transit, the driver rests, sleeps, or eats, fulfilling mandatory road safety rest periods while the train carries the vehicle through the mountain barriers. At the destination terminal, the process is reversed. The ramp is secured, the lashings are released, and the drivers simply start their engines and drive off the train, immediately resuming their journey on the highway. Because the cargo never leaves the trailer and loading requires no individual crane cycles, an entire train carrying dozens of trucks can be fully loaded and ready to depart in a matter of minutes. The industrial hubs of Germany and the manufacturing centers of northern Italy exchange hundreds of billions of dollars in goods every year. But standing directly between these two economic giants is one of the most formidable physical barriers on Earth, the ALPS. Because of this rugged terrain, the massive flow of north-south European trade cannot spread out over a wide network of highways. Instead, the geography forces millions of tons of freight to funnel through a remarkably small number of mountain passes. This concentrates the vast majority of transalpine road traffic into a few narrow, inhabited valleys. For the communities living along these corridors, this concentration of trade is a constant, disruptive presence. The valleys act as physical megaphone chambers, trapping the noise, exhaust, and soot of thousands of daily truck transits between steep rock walls. Local residents bear the direct environmental and safety costs of this continental trade pipeline, enduring constant congestion and the heightened risk of accidents on winding mountain roads. What is highly efficient for a shipping company in Munich or Milan becomes a daily hazard for the people living in the narrow mountain passes of Austria and Switzerland. Because these valleys have physical limits that cannot be expanded, the traditional approach of letting carriers choose their own routes and methods broke down. Allowing market forces to dictate shipping would mean clogging the Alpine passes to the point of collapse, destroying the local environment and the quality of life in these valleys. This geographic reality shifted Alpine freight from a simple commercial concern into a major regional dispute. Transport authorities and local governments realized that leaving transport choices entirely to individual road haulers was no longer sustainable. Direct intervention was the only way to protect the region, transforming how Europe managed the movement of goods across its borders. On February 20, 1994, Swiss voters passed the Alpine Initiative, inserting a binding mandate into their federal constitution to shift transalpine freight from road to rail. To enforce this transfer, Switzerland introduced the LS5A in 2001, a performance-related heavy vehicle fee. Rather than a flat toll, the LSVA targets trucks over 3.5 tons based on 3 specific variables: the distance driven within the country, the total weight of the vehicle, and its engine emission class. For older, high-emission trucks, the fee runs as high as 0.031 Swiss francs per ton kilometer, while newer Euro 6 models pay a reduced rate of 0.0239. For a standard 40-ton rig crossing the country, these charges add hundreds of francs to a single transit, transforming the basic economics of road haulage. Simultaneously, the Swiss Confederation enacted strict operating bans. Heavy goods vehicles are legally barred from the road network between 10 o'clock at night and 5 o'clock in the morning, as well as the entirety of Sundays and official holidays. Shippers cannot simply schedule around these windows without suffering significant logistical delays. East of Switzerland, Austrian authorities applied their own regulatory levers along the Brenner corridor. In 2026, Tyrol enforced 57 days of complete truck traffic bans for vehicles exceeding 7.5 tons, split between 36 days of southbound restrictions and 21 days northbound. These temporary bans are reinforced by a sectoral ban on the Inntal Highway, which prohibits trucks carrying specific bulk goods like waste, timber, and stone, unless the vehicle meets Euro 6 emission standards. These measures do not merely encourage rail transport through financial carrots. They construct a system of legal and financial penalties that make long-distance road transit through the Alps structurally uncompetitive. Demand for rail transport is not a natural market choice, but rather a direct product of state-mandated barriers on asphalt. This artificial market, however, relies entirely on the railway's ability to absorb the displaced road traffic, a task that immediately confronts the physical limits of the mountain infrastructure. The primary obstacle to absorbing this traffic is not the length of the trains, but the tight physical limits of the space above the rails. This is the loading gauge, the maximum height and width that a train and its cargo can occupy to safely pass through tunnels, under bridges, and alongside station platforms. There is no single, universal loading gauge across the European continent. Instead, the network is restricted by 19th century infrastructure. Early builders constructed masonry bridges, low tunnel arches, and narrow mountain alignments designed for a different era of transport, leaving very little vertical margin. Modern highway semi-trailers have grown to maximize cargo volume, with many now approaching 4 meters in height. If an operator places one of these standard trailers onto a conventional rail flat car, the combined height pushes the top of the trailer directly into the path of overhead structures. To double-stack containers in the American style, a railway requires an overhead clearance envelope exceeding 6 meters. For much of Europe, this vertical space simply does not exist. Rebuilding thousands of historic stone bridges, lowering track beds, and boring wider tunnels through solid mountain rock would require massive investments. Because of this, vertical clearances are highly localized. The permissible clearance envelope varies by corridor structure, wagon geometry, and specific route certifications. While select European routes have undergone expensive upgrades to accept taller loads, double stacking remains completely out of reach for the vast majority of the network. The infrastructure acts as a physical ceiling. Rather than removing these centuries-old bottlenecks to run larger trains, European operators had to design highly specialized, low-slung rolling stock that could squeeze standard highway trailers through the existing historic clearances. To fit a standard 4-meter-high highway trailer underneath the low overhead bridges and tunnel arches of Europe, railway engineers redesigned the train instead of modifying the truck. The result is a highly specialized piece of rolling stock that forces the cargo deck as close to the steel track as physically possible. Standard railway freight cars have a deck height of about 1 meter. A rolling highway wagon, however, drops its floor to just a few centimeters above the railhead, leaving almost no margin for error. To achieve this extreme clearance, designers discarded standard-sized railway wheels. Instead, they engineered specialized bogies containing small diameter wheels, often measuring only 36 centimeters in diameter. These tiny wheels must spin much faster than standard wheels to maintain track speed, creating immense friction and thermal stress on the axle bearings during transit. The mechanical layout is complex. Because the floor sits so low, the wagons require custom articulated joints and pocket designs that drop the trailer chassis down between the wheel sets. The wagon decks are fitted with steel wheel guides, lowerable securing devices, and heavy kingpin restraints. This custom hardware allows truck drivers to steer their massive vehicles directly onto the train and lock them in place under their own power, without the aid of terminal cranes. But this specialized design carries severe operational penalties. The tiny wheels wear down rapidly, demanding frequent inspections, precision machining, and frequent replacements. The mechanical complexity of the folding end walls, pivoting structures, and low-slung braking systems makes these cars expensive to build and exceptionally difficult to maintain compared to a basic flat car. The small wheel diameter also restricts the operating speed of these trains, typically capping them at 100 kilometers per hour. Outside of this highly specific Transalpine transit task, these specialized wagons have virtually no utility, making them an expensive, high-maintenance workaround for a permanent physical barrier. While specialized low-floor wagons became Europe's custom solution to tight clearances, the underlying concept of putting road transport on rails is not a European invention. In fact, American railroads pioneered this exact logistical shortcut decades before the modern Alpine corridors were built. In the early 1950s, major United States operators like the Pennsylvania Railroad, the Baltimore and Ohio, and the Southern Pacific launched what became known as Trailer-on-Flatcar Service, or TOFC, commonly called piggyback. To coordinate this rapidly expanding service, railroads pooled their equipment in 1955 under the Trailer Train Company. By the 1960s, piggyback had grown into one of the largest rail operations in North America, carrying hundreds of thousands of loads. But the American approach featured a fundamental design choice that set it apart from Europe's rolling highway. Instead of driving an entire truck, cab, engine, and driver onto the train, American operators uncoupled the trailer. The tractor stayed behind at the origin terminal. Only the trailer itself was loaded onto a conventional high-deck 89-foot flat car. The train handled the long-distance line haul, and a different local tractor hooked up to the trailer at the destination terminal to perform the final highway delivery. By leaving the heavy motorized tractor behind, American railroads avoided carrying thousands of pounds of non-revenue dead weight. The system used simple, low-cost flat cars with standard-sized wheels, bypassing the mechanical failures and extreme wear associated with specialized ultra-low-floor wagons. American railroads actively led this field, rather than ignoring the integration of road and rail. For 3 decades, piggyback service was a dominant intermodal model, proving that U.S. operators fully embraced moving road trailers on tracks, but adapted the process to carry only the cargo. In 1977, the Southern Pacific Railroad, collaborating with container pioneer Malcolm McLean, introduced a prototype well car that initiated a major shift in American logistics. This design moved beyond the limits of traditional trailer-on-flat car service by focusing entirely on the container. Instead of placing a wheeled trailer onto a flat car, operators began separating the cargo box from its road chassis and tractor cab. The box itself became the basic unit of rail transport, while the heavy rubber tires, steel frames, and mechanical running gear stayed behind at the terminal, no longer riding the tracks as non-revenue-producing deadweight. By stripping away the chassis, railroad planners and intermodal operators could stack these containers. A crane lifted the first container into a steel well car, lowering its center of gravity, while a second container was secured directly on top of it. 2 cargo units now occupied the same vertical footprint that previously held only 1 trailer. What began as experimental demonstrations in the late 1970s turned into rapid commercial expansion during the 1980s, as major railroads restructured their operations around this new format. The primary advantage was a massive increase in revenue-producing cargo over the same train length. However, this did not represent a simple, automatic doubling of capacity. Achieving these gains was a complex engineering task that depended heavily on specific equipment configurations, train consists, axle load limits, and overhead route clearances. If a line had low bridges or old tunnels, the double-stack configuration was physically impossible without major infrastructure modification. Yet where the clearance existed, the ability to move twice the payload on a single car body altered the cost structure of long-distance shipping, prompting American railroads to move decisively away from piggyback transport. This physical separation of the cargo box from its road wheel assembly allowed terminal operators to treat the container as a stackable block, optimizing terminal storage and maximizing train density in a way that trailer-on-flat car systems never could. On a trans-Alpine route of only 200 or 300 kilometers, terminal handling represents a massive portion of the total trip time. If a carrier must wait hours for cranes to lift, organize, and secure individual boxes, the railway loses its competitive speed against the open highway. The rolling highway solves this by turning the terminal into a simple driveway. A truck rolls on at one end and rolls off at the other, bypassing the crane entirely. For the driver, this short rail transit doubles as a legally mandated rest period, meaning both the cargo and the operator emerge at the destination ready to continue immediately on the road. The system works because it values the driver's time and keeps the vehicle moving through a localized bottleneck. But change the scale of the trip, and the economic equation flips completely. In the United States, a typical intermodal haul spans over 2,000 miles, crossing plains, deserts, and mountain ranges. On a trip of this length, the hours spent at the origin and destination terminals shrink to a tiny fraction of the overall schedule. Instead, the profitability of the run is decided almost entirely by line haul efficiency. Dragging a 40-ton motorized tractor, empty rubber tires, a heavy steel chassis, and an idle driver across several states is an enormous waste of locomotive power and track space. Over thousands of miles, the overriding priority is payload density, maximizing the actual cargo carried per foot of train. In this high-volume system, the operational penalty of carrying non-earning vehicle weight is far too high. Shippers and railroads cannot afford to haul the machinery that belongs on the highway. The convenience of a rapid, crane-free terminal loading process simply cannot justify the long-term fuel and equipment costs of hauling the truck itself. The regulatory frameworks of the two continents codified these different physical paths. In the United States, the major reform was the Staggers Rail Act of 1980. While not a single-cause explanation for the shift, this legislation granted private railroads the freedom to set market-driven rates, negotiate confidential service contracts, abandon unprofitable branch lines, and target capital where it was most productive. Under this deregulated system, intermodal service was evaluated purely on commercial return. Railroads could no longer afford to haul non-earning vehicle weight. They needed to maximize equipment productivity. This market drive naturally favored double-stack container transport, aligning train configurations with cargo density. Europe's rail environment, by contrast, is shaped by public policy goals, where market forces are deliberately steered. European authorities utilize road charges, night and Sunday truck bans, and environmental targets to push freight off roads and onto tracks. In this system, the rolling highway is supported not for its corporate profitability, but as a practical tool to manage regional transit. The claim that European rolling highways exist only through state subsidies is common, but the financial reality is corridor-specific. While public funding props up these services, state support has clear limits. For example, the Alpine service between Germany and Italy was terminated in late 2025 because network disruptions and capacity constraints made the run financially unsustainable despite ongoing subsidies. On the Brenner Pass, the service continues to operate because Austrian road restrictions and targeted slot bans make rail transit a necessary alternative for road haulers. These systems demonstrate the difference between two contrasting decision-makers. U.S. railroad managers optimize for the asset productivity of a private network, stripping away every pound of non-revenue weight. European public planners optimize for the social and environmental costs of a shared transit corridor, accepting the technical compromise of hauling the entire truck to protect their mountain valleys. North American railroads inherited a structural environment that, with some regional exceptions, offered more vertical clearance than European networks. Instead of accepting physical limits, operators spent decades physically modifying the right-of-way. They raised old highway bridges, enlarged masonry tunnels, and cleared thousands of local overhead obstacles along major routes. Establishing double-stack service required systematic route clearance rather than just acquiring new rail cars. The railroads rebuilt entire main lines to establish continuous high-clearance corridors, creating a highly permissive freight network where tall, stacked container trains could run without restriction. Europe took a different path, attempting to shoehorn tall road vehicles into legacy corridors. Although major programs target the establishment of 4-meter corridors capable of moving standard trailers, the work is highly localized and proceeds piece by piece. A single low bridge or historical tunnel can block an entire international route, forcing trains to detour or requiring operators to use specialized rolling stock. To bypass these historic bottlenecks permanently, European nations began building massive base tunnels. The 57-kilometer Gotthard Base Tunnel and the upcoming Brenner Base Tunnel project represent monumental engineering efforts to flatten the mountain crossings and enlarge clearances to modern continental standards. Yet because these mega projects are bound to specific, narrow mountain passes, they remain localized corridor solutions, rather than a continent-spanning, high-clearance network. While North American railroads reshaped their entire systems to remove physical boundaries, European public agencies must spend decades on localized, high-cost Alpine civil engineering works just to keep pace with modern trailer dimensions. The difference lies in how each system handles physical constraints. One rebuilt the network to fit the cargo, while the other continues to modify the train to fit the historic infrastructure. The financial weight of the rolling highway system falls heavily on its day-to-day operations. Unlike standard rail freight, a RoLa train requires a complex mix of assets. Custom low-floor cars demand constant maintenance, and as their small wheels wear down rapidly from high-speed rotation, requiring frequent shop visits for wheel turning and replacement. Terminal facilities are similarly expensive, requiring massive concrete pads to support 40-ton trucks and specialized ramps that must be maintained. Operators also bear the cost of hauling passenger coaches for the drivers, consuming tractive power without carrying any payload. These requirements create a steep operating cost for every single truck carried. Because the trains can only run between highly specific terminals, the system lacks the flexible routing of traditional road transport. This structural rigidity makes the direct commercial balance sheet incredibly fragile, even when public authorities view the service as an essential tool to protect mountain environments. This tension between public policy and commercial viability is causing the network to shrink. Reports of a complete Swiss-wide shutdown at the end of 2023 were incorrect, but major changes are unfolding. The joint venture Alpine announced it will end its long-running service between Freiburg, Germany, and Novara, Italy, on December 13, 2025. Alpine blamed heavy network disruptions and capacity bottlenecks on German and Italian lines, which made the corridor financially impossible to run, despite ongoing public subsidies. Meanwhile, the Gotthard route, operating under SBB Cargo, continues to run, showing that the system's retreat is localized rather than a total national collapse. The same economic struggle is playing out on the Brenner Pass. As the busiest Transalpine rail corridor, the Brenner route carries a substantial share of traffic, but the numbers show a widening gap between policy goals and financial realities. In 2025, Austrian Federal Railways transported 102,000 trucks on the Brenner RoLa. This is less than a third of the route's annual capacity of 300,000 vehicles. To keep the service running, the state provides subsidies of roughly €100 per truck, yet OBB Cargo still recorded a loss of €136 million in 2025. These deficits show that policy incentives cannot completely shield a complex transport system from market forces. While environmental mandates and truck restrictions can force traffic onto the rails, they cannot fix the underlying costs of carrying non-earning vehicle weight over short distances. The rolling highway remains an important tool for regional planning, but its commercial future faces constant pressure, as operators struggle to balance public demands with the hard realities of their operating budgets. Since its inception, the rolling highway has carried millions of complete trucks through the narrow mountain passes of Central Europe, physically lifting an entire segment of the road industry off the asphalt and placing it onto the tracks. To judge this system purely by its private balance sheet, or its high maintenance costs, is to judge it by a standard it was never designed to meet. The true measure of the rolling highway is found not in the operating margins of the railways, but in the physical environment of the Alpine valleys themselves. In Switzerland, this policy-driven approach has produced results unmatched anywhere else in the world. By the mid-2020s, Switzerland was sending a majority of its Transalpine freight by rail, consistently carrying around 70% of its total Transalpine cargo tonnage on tracks. It is a level of rail dominance that the United States freight system, despite its massive transcontinental corridors, has never approached. This historic achievement was not the product of a superior commercial logistics model. Instead, it was the joint output of aggressive road pricing, strict operating bans, clear environmental targets, and massive state-backed rail investments. The performance-related heavy vehicle fee, the legally mandated bans on night and Sunday trucking, and the construction of multi-billion-euro base tunnels worked in unison to squeeze road haulers off the highways. In this highly regulated environment, the rolling highway functioned as a key political instrument. It allowed governments to enforce strict environmental protections without completely cutting off the flow of international trade. For decades, the standard narrative has compared these systems as a simple contest of logistics, assuming that the American double-stack model represents the natural, superior endpoint of all freight evolution. But this perspective overlooks the fact that a transport system is always a reflection of the society that builds it. While the United States optimized its network for corporate efficiency, Europe used its railway as an extension of public policy, choosing to subsidize the movement of heavy road vehicles rather than accept the environmental destruction of its most vital trade corridors. Under this system, the primary beneficiaries are not the private shipping companies looking for the lowest cost per mile, but the communities and public institutions of the Alpine regions. For a family living in a narrow mountain valley, the technical inefficiency of carrying a motorized tractor and its driver on a train is entirely irrelevant. What matters is the quiet, the clean air, and the safer roads achieved by keeping thousands of heavy trucks out of their backyard every single day. Keeping trucks out of these valleys is a completely different objective from maximizing cargo volumes at the lowest possible commercial cost. Ultimately, the contrast between the European and American freight systems is a story of differing priorities. The United States chose to rebuild its physical infrastructure to remove constraints, lifting bridges and enlarging tunnels to allow double-stack container trains to maximize private asset productivity across a continent. Europe, facing dense populations and fragile mountain ecosystems, chose to adapt its trains to fit its historic constraints, accepting the high operational cost of hauling entire trucks to protect its land. The rolling highway is a compromise, but it is a highly successful one. It shows that infrastructure does not always have to adapt to the market. Sometimes the market can be made to adapt to the infrastructure. The question of why American railroads never adopted Europe's rolling highway system reverses the historical reality of intermodal transit. The United States did not fail to copy the European model. American operators pioneered the practice of carrying road trailers on trains in the early 20th century, used it for decades under the name piggyback, and abandoned the method when they developed a more productive alternative. The physical progression of intermodal freight in North America moved systematically from hauling the entire truck to stripping away the tractor and moving only the trailer, to finally discarding the road wheels entirely to stack the container. Each stage of this evolution removed non-revenue-producing deadweight, increasing the actual payload carried per foot of train. By the time Europe began establishing its rolling highways in the late 20th century, American railroads had already outgrown the concept of hauling heavy road machinery on steel tracks, viewing it as an unnecessary operational penalty. In the United States, private railroads prioritized long-distance logistics and equipment productivity. Operating across thousands of miles of open geography, they had the space and the commercial incentive to rebuild their main lines, raising old highway bridges and enlarging masonry tunnels to clear the path for taller, double-stacked container trains. This high-volume network grew out of a deregulated market where the main priority was reducing the cost per mile. Europe, by contrast, had to manage dense populations and fragile mountain ecosystems. Inherited 19th-century clearances, short border crossing distances, and the intense noise and exhaust in narrow mountain passes turned freight transport into a political dispute. European public planners could not wait decades to rebuild their entire continental rail network to accept taller trains. They needed an immediate, practical response to Alpine road congestion and regional emissions. The rolling highway became that necessary workaround. By adapting specialized, low-floor wagons to fit tight legacy clearances, European operators kept standard highway trucks moving without forcing trucking companies to purchase expensive new equipment. This system solved a political problem, prioritizing environmental protection over logistics density. While highly inefficient from a purely commercial shipping perspective, the rolling highway achieved what market forces alone could not. It successfully carried millions of trucks through the mountain passes, helping Switzerland achieve a rail share in transalpine cargo transit that the United States has never approached. This contrast highlights a deeper question about how societies manage physical limitations. One approach accepts inherited constraints, adapting equipment and operating rules to work around them. The other invests massive capital over decades to remove those constraints entirely, reshaping the infrastructure to allow the most optimal technology to operate. The choice between these two philosophies reveals what a transport system is built to protect, whether it is the asset productivity of a private freight rail network or the physical environment of the communities along the route. Today, global logistics faces a defining choice. As environmental pressures mount and trade volumes grow, we must decide whether to adapt our systems to existing constraints or rebuild our infrastructure to transcend them. The ultimate test of any network isn't its mathematical efficiency, but how well it serves the society that built it. Which approach do you think is more sustainable? Let me know in the comments.